hypothetically here. A could be something like t squared, t cubed, right? And B could be something like, t. So when you take the dot product of A and B, it's not a constant, it's a scalar function, right? It's actually, in this case, t squared plus t cubed plus t to the fourth, right? So like that's an example of what we're up against. But the answer, as it turns out, is this: dA dt dot B plus A dot dB dt. This is the product rule. And dA dt cross B plus A cross dB dt. Now the order of terms matters because the cross product is not commutative, right? So the dot product is pretty easy to prove. And maybe it proves, it's easy to calculate, let's say that, right? So what's the derivative of A dot B? Well, we're talking about the derivative of the sum over I of AI BI, right? But we can pull the derivative inside, right? And what is AI times BI here? Well, it's just an ordinary product of real valued functions, right? So I go back to calculus 1 and I go, oh, product rule, yay! And the product rule gives us, DAI dt times BI plus AI times dBi dt. But that is exactly dA dt dot B plus A dot dB dt, which is the alleged product rule I was just claiming. Yeah? So that wasn't too bad. Now, the cross product, if you were to do it using brute force notation, you'd have 6 different terms to take the product rule on, which would give you 12 terms. And after some rearrangement, you'd see it. Or you can use my notation that you'd rather ignore, but you shouldn't because it's actually very helpful. A cross B, of course, was the sum ijk epsilon ijk ai bj x hat k. Still true here. So when I calculate the derivative of A cross B, that gives me, the sum over I, j, k. I can pull the derivative, well, I'll just do it like this, ddt of epsilon I, j, k, ai, bj, x hat k. So that, so far, is the definition of derivative as I introduced it today, setting aside that unpleasant limit conversation we had. Right? I just said the derivative is defined by differentiating component-wise. Well, the kth component of the cross product is like, okay, fine, you got me. I should write this sum inside. Logically speaking, I'm supposed to do ddt of this thing. I and j. To be fussy, the sum over k is out here. Fine, you got me. But what's the deal with epsilon ijk? Do you guys remember how that goes? Does it have any time dependence? No, it's either 1 or -1 or 0, right? So you can pull that outside the derivative. And the derivative is linear, right? So the sum over ij pulls outside the derivative using the usual linearity. So we actually have epsilon ijk ddt of ai bj, and the x hat k just binds its own business out here. But you know the deal. Now we're to the derivative of a product of scalar functions. We know the product rule. So lo and behold, we've got the sum over I, j, k of epsilon ijk dai dt b sub j plus a sub I dbj dt, parentheses here, x hat k, right? And then, if you rewrite these as two sums, what you're looking at is exactly dA vector dt cross b plus a cross db dt, which is the product rule for the cross product. Yes, sir?
I have a question about the notation.
Sure.
So when I, j, and k are increasing, how does that work on the epsilon? Because it wouldn't be 1, 1, 1, 2, 2, 2, 3, 3, 3. And then how do you get like the mismatch to make the zeros and negatives?
So by definition, the epsilon ijk is only non-zero for 1, 2, 3, 2, 3, 1, and 3, 1, 2. Those are all 1. And then epsilon 3, 2, 1, epsilon, the other two, those are minus 1. So those are non-zero. There's 6 non-zero values. The other 21 of those are 0 by definition.
That's
So like your epsilon 1, 1, 1 is just 0. It's not there.
That's what I understand, but how, when you're like, if you were trying to use this notation to work out your problem, how does ijk increase? Like, do you just write out all the different possibilities of it?
Yeah, this sum over ijk is shorthand for the sum I equals 1 to 3, sum j equals 1 to 3, k equals 1 to 3, and all of those. And there's other theorems. You can commute the order of the sums. It doesn't change the outcome. And there's 27 possible terms there, yes.
Yeah.
Only 6 of which are non-zero, the ones which we care about. But there you go.
That makes sense.
Uh-huh. So, all right. I think there's a little bit more calculus to tell you about. I don't want to hurry through it today. I'll do it next time. But like we're missing, the fundamental theorem of calculus also extends to vectors, all right? So I talk to you about that tomorrow, probably. There's something really neat here to think about for a unit vector. What if we have a unit vector? What can we say about the change in a unit vector? Like a unit vector of time. Oh, you know what? I'm wrong. I do have time. I'm sorry, guys. I do have plenty of time. I will regret not doing the integration right now. We'll come back to that other thing I just talked about. That fits more naturally with a future lecture anyway. I just love it very much, so I want to talk about it as soon as I can. But I must resist the urge. So sorry. Integration. So, theorem, the integral from t1 to t2 of dr dt dt is equal to r of t2 minus r of t1. Also, ddt of the integral, say from t of r of tau d tau is equal to r of t. So those are essentially analogs to fundamental theorem of calculus. Well, fine. There's also FTC too. So sorry, guys. No, this suffices. I mean that's enough. We don't always write FTC2 in that format is what was tripping me up, but fine. All right, so like the second one, what do you got here? So we're talking about ddt of the integral, say from t naught to t of r of tau d tau. I'm going to give you guys a break from the summation notation and just give you a two-dimensional proof for a change, okay? So this is ddt, but admittedly this is an inferior proof. ddt of t x of tau d tau, integral from t naught to t y of tau d tau. Right? But if you'll allow me to save myself a little writing, how do we actually do that derivative? Oh, fine, I'll write it out. ddt, right? Integral from t naught to t, x of tau d tau, ddt, integral from t naught to t, y of tau d tau. So the integral of a vector is the vector of the integrals, excuse me, the derivative of a vector is the vector of derivatives, but here each component we're differentiating an integral, right? But FTC1 says what? We've got x of t, right? And y of t, also known as r of t. And so, like, there you go, that's the proof of 2. 1, if I'm talking about the integral from t1 to t2 of dr dt, that's the sum, I equals 1 to n, of the integral from t1 to t2 of dxi dt, right? But that is the sum over I of x sub I of t2 minus x sub I of t1 by the fundamental thermocalculus, the regular one. I missed my x hat I out here. And that rewritten is exactly r of t2 minus r of t1. So there you go. We have FTC 1 and 2 for vectors as well. So tomorrow I will tell you. Yeah, okay.
So how do you go from tau to t, from purple to black? How does that work?
Oh, well, tau is the dummy variable of integration. T is a fixed but arbitrary time here. So this, perhaps in a more reminiscent notation from your Calc 1 class, might have looked like this. We have d dx of the integral from a to x f of t dt, yeah? The critical thing there was that the integration variable is different than the bound. So since I'm using t for the bound, I can't use t for the integral. That's why I use tau, as opposed to x versus t. Of course, this is equal to f of x, just like this is equal to x of t. Yeah. Anyway, tomorrow we'll do arc length. All right, so yes, in 3D, woohoo!